This is the second video dedicated to Bessey Shuffle diagrams, so I thought we would quickly review a few definitions. A shuffle S is said to be a Bessey shuffle if and only if S preserves or inverts Bessey sequences. Recall, the Bessey sequences of order 8 are 1001, 0110, or its inversion 0110, 1001. Also recall the color coding that we've used to identify important position values relative to Bessey sequences. The two sets of interest to us are positions 1, 4, 6, 7, and its complement, the set of position values 2, 3, 5, 8. In our first video, we also explained the meaning of these sets of symbols here. Very quickly, this statement here simply affirms that the cards in positions 1, 4, 6, 7 stay within those positions somewhere. They might be moved around within those 4 positions or possibly stay fixed. And here, a complement being sent to a complement simply means that the cards in positions 2, 3, 5, 8 stay within those positions. Now that's in contrast to the inversion. Inversion occurs if the cards in positions 1, 4, 6, 7 get moved to positions 2, 3, 5, 8 in some assignment. And cards originally in positions 2, 3, 5, 8 get moved to positions 1, 4, 6, 7. And we call that an inversion. To tie in the notation of Bessey sequences on this playlist, recall that if we label the positions 1 through 8, the digits 0 and 1 for a Bessey sequence will satisfy one or other of these two possibilities. The ones are in positions 1, 4, 6, 7, as is the case in the top Bessey sequence right here. And the zeros are in positions 2, 3, 5, 8, 2, 3, 5, 8. The inversion of this Bessey sequence is what's found below, and the statements that we've made here simply get reversed. Namely, the ones are now in positions 2, 3, 5, 8, and the zeros are in positions 1, 4, 6, 7. Okay, the next Bessey shuffle we will look at is the one over here on the far top left. The J stands for judicious, and the RC simply reminds us that the stay-stack principle is in force. And more specifically, the cards are going to be dealt out into a number of piles for which the number of piles is a divisor of the packet size. Now the divisors of 8 are 2 and 4, setting aside 1 and 8. So here for this judicious RC, we will deal into 4 piles, and we will stack the piles in a way that we have not yet demonstrated within our discussion of Bessey Shuffle diagrams. Okay, so how this works then is we're going to deal out the cards into 4 piles. Once we've done that, we're going to stack the first pile on top of the third, the second pile on top of the fourth, and then, given those 2 piles, we will stack the left pile on top of the right. Now, the claim is that such a shuffle leads to the following permutation expressed in cycle notation. So why don't we go ahead and just kind of verify this. So if you remember, we began with Cauchy's 2-line notation for our permutation. So the top row will just be 1 through 8. So what we do is we work with an ordered packet, and I've just numbered these 1 through 8. We perform our shuffle, and then we look at what results. Okay? So the shuffle here is simply dealing into 4 piles, just like this, where it's understood that this is pile 1, 2, 3, 4. Okay, so according to our stacking here, we stack 1 on top of 3 and 2 on top of 4. And finally, we stack the left on top of the right. Okay, now if you've watched some of the other videos on Bessey sequences, we've referred to this as the leapfrog shuffle, where you're leaping over the neighbor of each pile, moving from left to right in this case. Okay, so what does that result in? What do we finish with here? Looks like it's a 5, 1, 7, 3, 6, 2, 8, 4. That's what we get. 5, 1, 7, 3, 6, 2, 8, 4. Okay, so that is the new ordering after that shuffle has been applied. Okay, now given that information, we can now rewrite that 2-line notation into 1-line notation, also called cycle notation. Okay, so how this works is you begin with 1 up here. 1 goes to 5, so I have an arrow from 1 to 5. 5 goes to 6, 5 goes to 6. 6 goes to 2, so I have an arrow from 6 to 2. 2 goes to 1, so it wraps back around. So that gives us a 4 cycle. So we can compress all of this information, what's happening with those 4 values, to just this set of symbols here. Okay? Now for the remaining values, we get the following. If we begin at 3, 3 goes to 7, so we have an arrow there. Where does 7 go? 7 goes to 8, 8 goes to 4, and then 4 goes to 3, which wraps around, so that closes that cycle. So we can compress all of that information into this set of symbols right here. So 3, 7, 8, 4. Now color-coded, we obtain the following. So if we just rewrite the terms in the cycle notation of our permutation, we'll obtain the following. Remember from earlier, 1, 4, 6, 7 are color-coded black. 2, 3, 5, 8 are color-coded red. So if we go through and perform our color coding, we'll see that black 1 goes to red 5, which goes to black 6, which goes to red 2, which wraps around and goes to black 1. Red 3 goes to black 7, which goes to red 8, which goes to black 4, which wraps around to red 3. So what's happening here is each black value is being assigned to a red value and vice versa. So each value gets sent to a value of the opposite color. In other words, inversion has occurred. And we can see that in the diagram on the left. So in our very first video, we showed you how to draw these. So 1 goes to 5, so we have an arrow from 1 down to 5. 5 goes to 6, so we go up to 6. 6 goes way over here to 2, so there's an arrow from 6 to 2. 2 goes up to 1, straight up like that. And that completes that cycle, actually. And we also call that an orbit. The set of values 1, 2, 5, 6 form an orbit, meaning they get assigned to values within that set. And then the remaining portion of the diagram, if we begin at 3 right here, 3 goes to 7. So 7's up here. 7 goes to 8 there. 8 goes all the way down here to 4. And then 4 goes to 3. So it just goes right there and completes that cycle. Now I have a note here at the bottom that this particular shuffle is the inverse of 42. So that is a shuffle that we'll be looking at later in this little series on Bessey Shuffle diagrams. So I'll remind you of that when we get to Shuffle 42. And then up here I have a summary of the fact that inversion occurs. 1, 4, 6, 7 get assigned to 2, 3, 5, 8 in some order, and 2, 3, 5, 8 get assigned to 1, 4, 6, 7. So inversion, in fact, does occur. Now, what that means, if you remember, when it comes to Bessey sequences, so why don't we just tie that in quickly again from last time. So here is the kind of quintessential Bessey sequence if you want to begin with a 1. So 1, 0, 0, 1, 0, 1, 1, 0. The claim is that this shuffle will invert this. Well, inverting this simply means that we'll replace zeros for ones and ones for zeros. And in particular, it just means that we're going to get the second Bessey sequence of order 8, which is 0, 1, 1, 0, 1, 0, 0, 1. So let's go ahead and just show you that inversion, in fact, occurs. So once again, what was this shuffle? We deal into 4 piles, like so, from left to right. And then we're doing this kind of leapfrog. We're going to go take this one, this is pile 1, hops over and gets stacked on top of pile 3. 2 hops over and gets stacked on top of pile 4. And then in this particular shuffle, we're going to stack left on right. Okay? So the claim is we should now get 0, 1, 1, 0, 1, 0, 0, 1. Okay? So that is what we get. Inversion, in fact, occurred. So you may want to think about the practical value of knowing inversion occurred. So for example, if all of the 1s were the aces, the 4 aces, and the 0s were the queens, then if we had started with the 1s on top, like we did, okay, so if we started with an ace on top, that would mean we'd have a queen on the bottom. So this is where so once again, this is where we started before the shuffle, right? This is where we started. And so because inversion occurred, what that will mean now is instead of an ace being on top, after we perform this shuffle, we are guaranteed to have a queen on top with an ace on the bottom, okay? And so at the end of this video today, we'll show you a simple application of all of this that involves just ordinary cards. Okay, let's look at the second shuffle, the top row, but the one on the right. The only difference here, if you contrast it with what we just did, the stacking will be the same, involving this leapfrog technique, but we will then stack the right pile on top of the left. Okay, so that's the only difference. And the claim is the cycle notation for this permutation is the following. Parentheses 1, 6, and then a set of parentheses 3, 8. Okay, so let's just quickly step through this. Okay, so you just start with 1 through 8, as we have. Perform the shuffle itself. So we're dealing into 4 piles. We're going to do the leapfrog. So 1 goes and gets stacked on top of 3. 2 jumps over 3 and gets stacked on top of 4. Now we stack the right pile on top of the left. Okay? And as you might imagine, that's going to change the order of the cards from what it was in the first example today. Okay? So this is what we get. We get 6, 2, 8, 4, 5, 1, 7, 3. Okay? So that is how I got Cauchy's 2-line notation for this permutation. That bottom row right there is 6, 2, 8, 4, 5, 1, 7, 3. And we can change or convert this to cycle notation, which is far more compact. So what we do here is you just look at 1 on the top row. Where does 1 go? 1 gets sent to 6. So 1 goes to 6. 6 goes to 1. So it wraps around. So we get this little 2 cycle, also called a transposition. So 1 and 6 just switch places. Now 2 goes to 2. So it's a fixed point. 3 goes to 8, and 8 goes to 3. And then it wraps around. So we get a second transposition, or 2 cycle. And then from there, we just get a bunch of fixed points. 4 goes to 4, 5 goes to 5, 7 goes to 7. Okay? So if we color code all of this, what we'll get is the following. Remember, 1, 4, 6, 7 are black, 2, 3, 5, 8 are red. So we will not have, quote, inversion this time. So black 1 goes to black 6, and then black 6 goes to black 1. Red 3 goes to red 8, and then that gets sent to red 3 again. Now, red 2 stays where it is. It gets sent to itself. Black 4 gets sent to itself. Red 5 gets sent to itself, and black 7 gets sent to itself, okay? Now, we've mentioned this before. Normally, we do not write single cycles or one cycles when we're representing a permutation using cycle notation. As long as we know the size of the set we're working with, we can actually drop these little one cycles. They are also called fixed points because that's what they do. Whatever's in position 2 gets returned to position 2. Okay, and same thing for position 4, 5, and 7. So here, each value gets sent to a value of the same color. So there's no inversion here. Going back to our sets here, what we're saying is these position values, or the objects in these positions, will be sent to these same position values, even though they might get reassigned within that set of values. The same thing here for a complement. The objects in positions 2, 3, 5, 8 will stay somewhere in positions 2, 3, 5, 8. Okay? So there's no inversion. Inversion happens when this occurs. So it's exactly preserved. Now, what that will mean for our Bessey sequence, and I think you can probably begin to anticipate this now with all of the practicing that we've been doing, is if we start with our the Bessey sequence 1, 0, 0, 1, 0, 1, 1, 0, and we perform this shuffle, what will happen is we will get that same form back. It won't be inverted. Okay, so we do this leapfrog. 1 gets stacked on top of 3, 2 gets stacked on top of 4, and then it's right on left. So we will get back to 1, 0, 0, 1. Move that over. 0, 1, 1, 0. Okay? Now, it is true that some of these cards, some of the ones have moved around among themselves, and some have stayed fixed. And some of the zeros have moved around among themselves, and some have stayed fixed. Okay, let's take a look at our third Bessey shuffle for today. Now remember, a shuffle is a Bessey shuffle if it preserves Bessey sequences or inverts. So it needs to preserve or invert Bessey sequences. Well, the claim is all of the shuffles that we're going to feature in this little series are shuffles that preserve Bessey sequences. So therefore, by definition, they are Bessey shuffles. So this next one is going to be also a dealing out into 4 piles with judicious stacking. Now, one of the reasons I chose that word is you can't randomly stack these 4 piles. Just randomly stack them and expect that any particular structure will survive that, because it won't, okay? But this is far more complicated than just stacking from left to right or right to left. You're doing kind of this leapfrog stacking. But nonetheless, this stacking will preserve the fundamental structure of Bessey sequences, which is amazing. Okay, so the claim is the cycle notation for this permutation is the following. In fact, it's a product of 4 transpositions. That's interesting. We're just switching the objects in pairs. That's all we're doing. Well, let's see that happen here. So we begin with our ordered packet, as always, 1 through 8. We'll perform the shuffle. So this is pile 1, 2, 3, 4. 3, 4. Very good. Now, what we're going to do is we're going to stack. This is 4. 4 goes on top of 2. 3 goes on top of 1, and then we will stack the right pile on top of the left. Okay, so once again, this is the leapfrog stacking that I've used in the Bessey sequence videos on this playlist. Okay, and now finally we're going to stack right on left. Okay, so what does that give us? What's the new ordering of the cards? Okay, well, this is what we get. So let's just check that that's what I got here on my piece of paper. So we started with 1 through 8. We performed the shuffle, and we got the new ordering 84627 and that's what we got. Okay, now changing that to cycle notation, we find quite readily that we get a bunch of transpositions. 1 goes to 8, so we have an arrow from 1 to 8. 8 goes to 1, so that wraps around, so that is completed. That's a little 2 cycle. 2 goes to 4, we have an arrow from 2 to 4. 4 goes to 2, so that wraps around. That's another transposition. 3, what does 3 do? 3 goes to 6. 6 goes to 3, so that wraps around. And finally, 5. 5 goes to 7. 7 goes to 5, that wraps around, so we get a 4th transposition. Okay? So what happens with the color coding here? Did inversion occur, or did we just preserve these sets A and A complement? Well, inversion did occur, right? Because remember, 1, 4, 6, 7 are designated as members of the set A and are color-coded black. Position values 2, 3, 5, 8 are members of the complement of A and are color-coded red. Okay, so this truly is an inversion. Each value gets sent to a value of the opposite color. And so I don't know if we'll demonstrate it, but what that means, and this is something you can try on your own, it won't take much work, but if you start with a packet like this where you have 1, 0, 0, 1, 0, 1, 1, 0, and you perform this shuffle, you'll end up getting 0, 1, 1, 0, 1, 0, 0, 1. So inversion occurs. And I should point out the graph for the 7th shuffle. So it's over here, bottom left. As we've seen, we're looking at 4 transpositions. What you should expect to see are double arrowed lines between some red value and some black value. Okay, so 1 goes to 8, 8 goes to 1, 2 over here goes to 4 down there, and 4 goes to 2. 3 over here goes to 6, and 6 goes to 3, and then 5 goes to 7, and 7 goes to 5. And then we've indicated that inversion occurs. I want to quickly apologize because for some reason I skipped over the graph for number 6. If we go back to 6, if you remember, we got product of 2 transpositions with the remaining 4 values being fixed points, 2, 4, 5, 7. So this is what the shuffle diagram would look like for shuffle 6. And as pointed out up here, inversion does not occur. Okay, so just wanted to point out the graph for shuffle 6. Okay, for our last shuffle today, it's on the bottom right quadrant of our graph there. We're looking at a, quote, leapfrog shuffle as well, but this time we'll finish with the left pile being stacked on top of the right. Okay, so to quickly demonstrate this, we'll go ahead and begin with 1 through 8, as always. So here we deal into 4 piles, and then we're going to stack the 4th pile on top of the 2nd, so we kind of do a leapfrog, and then the 3rd leapfrogs over that one and lands on the 1st, 3rd on 1st, and now we're going to stack left on right. Okay, so what is the new ordering that we get from that? What is the new ordering of the cards? Well, here it is. 7, 3, 5, 1, 8, 4, 6, 2. 7, 3, 5, 1, 8, 4, 6, 2. That is the new ordering. This 2-line representation for the permutation can also be written in cycle notation as follows. 1 goes to 7, 7 goes to 6, 6 goes to 4, and 4 goes to 1. Looks like I left that off. 4 goes to 1. So 4 wraps around to 1. So we get 1, 7, 6, 4. And then what do we get for the other remaining values? Well, 2 goes to 3, 3 goes to 5, 5 goes to 8, and then 8 goes to 2. It wraps back around to 2. So we get this 4-cycle 2, 3, 5, 8. Now if we color code these, we'll immediately detect that inversion has not happened here because 1, 7, 6, 4 are all, quote, color-coded black, and 2, 3, 5, 8 are all color-coded red. So there's no inversion. So each value gets sent to a value of the same color. Okay, now the graph for this one is an interesting one. It's on bottom right. So 1 goes to 7, So you start here, there's an arrow from 1 to 7. 7 goes to 6, so you just go straight down there. 6 goes down to 4 on the right. 4 goes up to 1. That completes that cycle. And so we would call that an orbit, by the way, as well. The set 1, 4, 6, 7. Think of those values as just being moved around among themselves, permuted, assigned to one another. And then for the second term in our cycle notation, 2, which of course is over here, goes to 3. So it goes straight down. 3 goes to 5, so it's kind of down here. It's hard to see. And then 5 goes up here to 8. Okay, so that completes that 4 cycle. Now, before we look at a application of this, I guess I should also point out the order of each of these shuffles. So let's start with the first one, number 5. We have a pair of 4 cycles. So the cycle notation for this permutation breaks up into 2 terms. Each one has cycle length 4. So what that means then is if we perform this shuffle 4 times, it returns the packet to its original order. Now contrast that with the one over here, number 6. It's the product of 2 transpositions with the other values staying fixed. Well, this shuffle will return the packet to its original order after just 2 applications of the shuffle. So you perform this shuffle twice, you get back to the original order, which is also true for number 7, shuffle 7, because we have a product of 4 transpositions, but each one of these individually will, quote, reset the values to where they started after 2 applications of this shuffle. So performing this shuffle twice resets the packet to its original order. And then finally, the last one here is similar, analogous, I guess, to number 5 up here, where you would need to perform this shuffle 4 times to reset the packet to its original order. Okay, so let's take a look at a simple application of all of this. So what I have here is I just have 4 black cards and 4 red cards. Now, I don't know if you've ever heard of the phrase opposites attract. Opposites attract. Okay, so that's a phrase that's often used. People claim that that is in fact true in general. Opposites attract. Okay, so what we're going to do is we're going to perform each of these shuffles, and we can actually perform them multiple times if you would like. But so if you were here, I would have you randomly choose shuffle 5, 6, 7, or 8 to do. Maybe you'll want to do number 6 first. Okay, that's fine. Okay, so we'll do number 6 first. Okay, so take a look at number 6. What does 6 say? It's a leapfrog. We're going from left to right. 1 goes on 3, 2 goes on 4, and then we're stacking right on left. Which shuffle would you like to do next? Number 8? Okay, we'll do that one next. Try not to go off the screen too much. Number 8, what does number 8 say? Oh, it's 4, goes on top of 2. It's a kind of a leapfrog from right to left. And then we finish with left pile on top of right. Okay, now we've finished shuffle 8. Want shuffle 5 now, which we haven't done. Okay, that's just fine. Okay, so shuffle 5. We're stacking the first pile on top of the third, second on top of the fourth, with the left pile being stacked on top of the right. And then why don't we finish with shuffle 7, which we haven't done yet with this particular packet of cards. Very good. And so here we're stacking from right to left, but with this leapfrog. You're stacking 4 on 2, 3 on 1, and then the right pile gets stacked on top of the left. Now the reality is you could have the spectator choose any one of any of these 4 shuffles in any quantity and in any order. And you will still have significant knowledge of the structure of this packet. In particular, I have enough knowledge, and you would too, to do the following, to essentially confirm the claim, the aphorism that opposites attract. Okay, so this is our little proof that despite all of that mixing and randomization decided by you, the spectator, and what I've done here is I've just put out pairs of cards. Well, if it's true that opposites attract, something special should have happened. Let's find out. Black card and a red. Black card and a red. Red card and a black. And a black card and a red. Look at that. That is indeed proof, I think, that opposites attract. Okay? So, of course, now how you do this, let me just explain the mechanics if you aren't sure how to do this. If you've been watching the videos on Bessey Sequences, you probably can do this without any further help. So this is where we started. Okay? So this is where we started with 4 red and 4 black. Or you could start with 4 black, 4 red, it wouldn't matter. Okay, and then if you remember, what I did was I did something called a triangle deal. Now this is a clever little thing that Werner Miller came up with. So if you just deal kind of clockwise, so I'm going to deal into a triangle like this. And then you simply stack in opposite order, the opposite orientation. So now we'll go counterclockwise. That is guaranteed to take the packet structure that we just had of 4 red and 4 black. It will convert it to a Bessey sequence relative to card color. So we have a black, red, red, black, red, black, black, red. So that's kind of like having a 1, 0, 0, 1, 0, 1, 1, 0. So it's of the correct structure type. Okay? Now, the claim is, because these are Bessey sequences that we're studying in this little series, each and every one of these shuffles over here will preserve or invert it. Now, we know what number 5 does. In fact, maybe we'll try to do it in the order that we did. So I think we did 6 first. Well, performing that, we don't actually invert anything. We'll get back to the same reds and blacks as configured at this moment right now. And then I think we went down to number 8. Same thing here. We don't invert. Okay? So the red cards get moved among themselves. The black cards get moved among themselves. I think we did 5 next. But 5 inverts it. Okay? So the reds and blacks kind of switch places, which is not a problem. And then down here, number 7 inverts it. So really the net effect, 2 of these leave it as is relative to its Bessey structure. And 2 of these convert it to the inversion of the initial Bessey structure. Okay? So what that will mean then is we started, if you remember, when I showed the organization of the cards after the triangle deal, we had a black, red, red, black, red, black, black, red. So you can rewind the video and confirm that yes, that is indeed the case. So 2 of these shuffles inverted this, where blacks and reds switch places. Well, if you do that twice, you get back to this kind of organization of the cards. Black, red, red, black, red, black, black, red. Well, from there, what did I do? I just did a Klondike. And there's a whole bunch of ways. There's almost countless ways to use your knowledge of the organization of these cards to put them into whatever piles you want. I could have put them into a pile of 4 red cards and a pile of 4 black cards if I wanted. Or I can put them into pairs of opposite colors and do that in a number of different ways. Now, a slick way to do it is just use the Klondike Shuffle, which is what I did. And if you remember, the Klondike Shuffle, it pulls the top and bottom cards off as 1. Well, that means that the black 4 is going to be paired with the red ace. Now, as you go down, so that's set down as a pair, and those are of the opposite color. Now, the next card down is red 2 and black 3. Those get pulled off. A red 9, a black ace. Those get pulled off. And then we get a black 8 and a red 5. Okay? So when this is turned over, now we normally wouldn't have shown the spectator, kind of the intermediate steps. But we know, because it's a Bessey sequence, it doesn't even matter what kind. and it doesn't really matter whether the top card begins black or red. If you pull these off with the Klondike Shuffle, you're guaranteed to get pairs of opposite color. Okay, so that's just kind of a fun little application. And once again, the amazing thing is you can perform all or any of these 4 shuffles in any quantity and in any order forever. You just do it all day long if you want. At any point, you could stop using one of these 4 shuffles and finish with this kind of ending, where each pair is guaranteed to be of the opposite color. So anyway, that's just kind of a fun little application that leverages your knowledge of Bessey sequences and these special shuffles that either preserve or invert Bessey sequences. So thank you for watching, and next time we'll take a look at the following 4 shuffles. Here they are on the left. Some pretty crazy ones result from the Monge shuffle, as we'll see. In fact, this bottom left one just shows the highly chaotic nature of a Monge shuffle. But nonetheless, it will not destroy the fundamental organization of a Bessey sequence. It does invert it, which poses no problems for us. And at the end of this whole series, I'll show you one or more examples of shuffles that are not Bessey shuffles. Namely, they do not preserve or invert Bessey sequences. In fact, if you want to play with one right now and test it for yourself, the Australian under-down is one such shuffle. Now, the down-under is a Bessey shuffle. It doesn't harm Bessey sequences, but the under-down does, as we'll see. So not every shuffle under the sun is, quote, a Bessey shuffle. But boy, how surprising it is to find that a majority of the systematic shuffles that are used for small packet sizes are indeed Bessey shuffles. That is one of the most surprising consequences of all that we'll show you in this series on Bessey shuffle diagrams. So thank you for watching, and take a look at the next video in this series